So today we're starting chapter 3. The way chemistry seems to go in most textbooks is we'll have a chapter that's got lots of math, like chapter 2 had, and then we'll have a chapter that doesn't have much math. The first part of chapter 3 has no math in it, so that'll make some of you really happy. We're going to talk about matter and energy. Here's a picture of a room. You can also look around this room. Anything that you can see in this room or in that picture is made of matter. Okay, in science we use the word matter a little bit differently than we do in real life. In real life we say, well, what's the matter? You know, what's bothering you? What's troubling you? And in science we use it to refer to things that have substance. And when we look, for example, here's a bottle of water. Here's an illustration of what the particles, the molecules in that water look like. Here is a golf club, a graphite golf club, and in the shaft, it's made out of carbon. The differences in the properties between this golf club, which is very strong and holds its shape, and in water, which is, runs all over the place and is clear, and you couldn't hit a golf ball with that to save your life. The differences between the properties of those substances come about from the differences in the particles. Okay, and that's what chemistry studies. So how can we define matter? One way to define matter is that matter is anything that occupies space and has mass. Okay, and some of these things are easy to see with your naked eye. Ooh, I used the word naked. I've got a 4-year-old. That's the sort of thing we have at home. Some types of matter are easily visible. What is something in this room that is matter that we can see? I can't hear you. The walls. Okay, so walls are made out of matter. Anything else? The stapler. Okay. So those are examples of visible matter. Okay, other types of matter are impossible to see without magnification. What do you think is in this room that is matter? It occupies space and has mass, but we can't see it. Air. Can you think of anything else? Do you think there are any germs in this classroom? Probably. So things like bacteria. Bacteria is matter, but we can't see it. Okay? That fly, the fly that's in my face, the fly is made up of matter. Your bodies are made up of matter. Okay? So pretty much anything you can see is going to be matter. Matter looks like it's smooth and continuous. We look at the bench top and it's pretty smooth. But actually matter is not continuous. It's made up of little tiny particles. Okay, so I tried to come up with some good analogies yesterday for this and they were kind of lame, but we'll go with them anyway. So matter is composed of atoms. Atoms are submicroscopic particles. Sub is a prefix that means below. A submarine goes below the sea, right? So submicroscopic means it's smaller than what you can see with a microscope. And these are the fundamental building blocks of matter. So, I don't know, Legos just end up being a good analogy for atoms. So you can think of atoms as being a little bit like Lego bricks. Has everybody here at least played with Legos once in their life? Okay, we have a ginormous collection. We've had 5 boys collecting Legos. The girl has some too. We've got lots of Legos. They come in all different shapes and sizes and colors, don't they? And you can build different things out of them. Now, there's a really cool amusement park in San Diego called Legoland. And at Legoland, I should have a picture in this lecture. At Legoland, they have recreated lots of monuments and different famous structures around the world out of Legos. They have the Taj Mahal made out of Legos, and they have Mount Rushmore. And if you stand back far enough, if you look at it from a distance, it looks pretty smooth. That it's, because these things, Mount Rushmore is like this tall, about as tall as I am, made out of Legos. Actually, it might be a little bigger than that. And so you don't really see that there's these individual little bricks, but then you go up and look closely at it, and you're like, oh, that's not continuous. It's little tiny bricks stuck together. I guess another example might be if you take a digital photograph and you zoom in on it. And you zoom in and in and in, eventually you'll get down to where you can see the pixels. And you see that that picture is actually made up of little tiny squares. Matter is the same way. All matter is made up of atoms. And so it's not actually continuous. It's all these little pieces stuck together. So atoms can bond together to form molecules. So a molecule is two or more atoms. A lot of molecules are only two atoms, but you could have like 500,000 atoms in one molecule. They're joined together in a specific arrangement, and that's what we mean by the term molecule. So here's just some illustrations. Important that all matter is ultimately composed of atoms. So even things where the particles are molecules, those molecules are composed of atoms. So here we have a soda can made out of aluminum. Okay, aluminum is an element, and it is composed of aluminum atoms. And so if we blow this up, we call this looking at the particulate level. This is the macroscopic level, which is what you can see with your eye. In between would be a microscopic level. The biologists care a lot about microscopic levels. In chemistry, we just kind of skip that because this doesn't really help us much. You go down to the particulate level, where we're looking at the individual particles, and we see all of these are all the same. They're aluminum atoms. So some substances, the atoms are the independent particles, but in other substances, they bond together to form molecules. So here is an illustration of isopropyl alcohol. And if we zoom in on it, we see that all of these individual particles are free to move about, but each particle is the same, and each particle is composed of several atoms. Can anybody see the mistake in this picture? It has to do with the name of the alcohol. What does it say on the bottle? On the bottle it says pure ethyl alcohol. Right here, pure ethyl alcohol. And up here they're giving us an illustration for isopropyl alcohol, and they're saying this is isopropyl alcohol, rubbing alcohol. Isopropyl alcohol and ethyl alcohol are not the same thing. This drives me bananas. With very high-tech equipment, we can visualize atoms. Okay, the scanning tunneling microscope uses a little probe and measures the current between that probe and the surface, and uses a computer to generate an image. Okay, it's not like we're looking through and we're actually seeing something, but it's using electrical information to generate an image for us. And this is the sort of thing we get. This is the best sort of picture that we can get of atoms. It's still pretty fuzzy and rough. But these blue bumps here represent individual atoms. This one's cool. This is a scanning tunneling microscope image of a DNA molecule. So the DNA molecule is in yellow. And a DNA has a double helix structure, and you can kind of see that. Here's one of the helices, and here's the other one. Oops, I messed that one up a little bit, but you get the idea. You can kind of see the helix in there. That is the DNA that's in your body and controls what color your hair is and what color your eyes are. So we do have evidence that these molecules and atoms actually exist. Okay, so scientists classify things. We've got all these bits of information, these observations we've made, and so we classify them to try to make sense out of things. So we're going to classify matter. We can classify matter by its state. The three common states of matter are solid, liquid, and gas. And it's useful to look at water because water is one of the few substances that we're familiar with in all three of its states. Okay, ice. In the summer we like ice. I have ice in my drink here. Ice is water in a solid form. And when water is in the liquid form, that's when we call it water. And if you heat water, it will evaporate or boil, vaporize, and you have water in the gas state. There is gaseous water in the air here. There's not nearly as much as there is like in Florida or even in Minnesota where the humidity is high. Humidity is the water in the gas state in the air, and there's always going to be a little bit. So we need to talk about and we need to understand what the particles are doing in these different states. If we look at the solid, here's the illustration, we see that these particles are close together. And in the liquid phase or liquid state, they are also close together. Some books call them touchingly close. Okay, they're close enough that they can touch each other. In the gas state, they are farther apart. And actually, this is not to scale. The distance between these is a lot larger. So that's one difference. The other difference is how the particles can move relative to each other. In the solid, they are fixed relative to each other. In the liquid, they can move around, and in the gas, they can move around. So I used to use an analogy of cows, but then one day I just came up with one for students. So we're going to use the student analogy for states of matter. So right now, the people in this classroom are in the solid state because you're sitting in chairs and you're not moving about relative to each other. Okay? The person next to you is staying next to you all the time. Now, are you all sitting perfectly still? No. If we were all perfectly still, we'd keel over and die because we wouldn't even be breathing. Okay? When you breathe, you move a little bit. So we're fidgeting a little bit, we're scratching our heads, maybe we're taking notes, that's a good idea. You're moving a little bit. In the solid state, atoms and molecules are not stationary, but they are vibrating. So they're just, think of them as fidgeting in their seats. But it's like assigned seating, you're in your seat, you're not allowed to get up, but you can wiggle around. Okay? In the liquid state, students in the liquid state is more like what we have in lab, where we're all kind of milling about the classroom, right? I'm working on something and I have to go to the cart and get my chemicals and I come back and we're just moving about. That's what liquid particles do. They move about. They're still close together though, aren't they? The gas state for students is when class is over and you go out the doors and you go off in all kinds of different directions. And you maybe don't even see each other, you don't interact with each other at all. So you're much farther apart and you're moving completely independently. So 3 states of matter, 3 states of students. So this just kind of goes over what I've said. So in the solid, the particles are very close together. So they're close to each other and they are in fixed locations. The particles are going to vibrate or oscillate, but they're not going to move around. And so solids have fixed volume and they have a rigid shape. And these are things that are important for you to recognize about the solid state of matter. And if you think about ice and water and steam, it can help you to remember this. Think about an ice cube. You make an ice cube in an ice cube tray and you take it out of the tray and you put it in a big bowl. Does its shape change? No. It's still shaped like an ice cube. Does its volume change? Does it get bigger or smaller? No. Solids retain their shape and their volume. There are 2 kinds of solids, general categories, crystalline solids and amorphous solids. In a crystalline solid, we see that we have a regular repeating order. Okay, so this is a little more like a traditional classroom where you have all of the desks lined up in rows, and there's a pattern, and it's repeating. That's a crystalline solid. There's order. Amorphous, it's helpful to understand prefixes. A is a prefix that means without. Morphous has to do with shape. You know, you think about the superhero cartoons and stuff. You know, this guy has this superpower that he can morph, right? What does that mean? He can change his shape. So amorphous means without shape. This is an illustration of the particles in an amorphous solid. So right now you guys are more of an amorphous solid because there's not really a pattern to how you're sitting. I mean, we're kind of around these weird benches, but we're not sitting in ordered rows. So things like sodium chloride, diamonds, other gemstones and minerals tend to be crystalline solids. If you go home and you look at the salt in your salt shaker, look at the little tiny pieces. They're all little cubes. The manufacturer of this salt did not go out of their way to make little tiny cubes for your salt just because. Salt forms little tiny cubic crystals because of its nature, it's crystalline. If you look at something like flour does not have little crystals. It's just little specks, little randomly shaped specks. It's amorphous. The more traditional examples of something that's amorphous are rubber and glass. So two kinds of solids. So the liquid state. So here, in a liquid, the particles are still close to each other, but they're free to move around. Okay, so that's during lab. We're all just milling about. Liquids have a fixed volume because they're still close together. If we think of the volume of the students in this class, the volume that you're occupying, does the volume that you occupy change much from when you're all sitting in lecture to when you're milling about in lab? It doesn't. You know, we're taking up about the same amount of space. When we leave the classroom and go out into the gas state, now if we're trying to, put a bubble around us, we would take up a much larger volume, especially if somebody decides to go to San Francisco for the weekend. We'd have to include them, and they're like 150 miles away. So the gases change change volume. Liquids do not because the particles are still close together. So liquids assume the shape of their containers. So their volume doesn't change, but their shape does. So think about that ice cube, and you melt it, and you take it from maybe a little tiny cup, and you pour it out onto the table. Does its shape change? Yeah. Before it takes on the shape of its container. So in this little tiny, maybe it's in a little shot glass, a little tiny cup, and then you pour it on the table, and it spreads out into this really thin layer all over the table. Its shape has changed. Has the volume changed? No. You can it doesn't work when you pour it on the table, so that was a bad example. If you take some water in a large, shallow bowl and pour it into a tall, skinny cup, its shape changes, its volume doesn't. If you measure it either way, it's going to have the same volume. So that's important to understand about liquids. Okay, gases. The particles, the molecules are separated by large distances, and they're free to move. So the free to move is in common with the liquid, but now instead of being close together, they're far apart. Because of that, gases are compressible. So if we look at this illustration here, here's an illustration of a solid inside of a piston. And if we push down on that piston, it's not going to go anywhere because these little particles in here can't go closer together. This is an illustration of a gas. In a gas, there's a lot of empty space. And so if you press down on that piston, you can squeeze the gas closer together and compress it because you just push the particles closer together. Gases are compressible, liquids and solids are not. So gases assume the shape of their containers and the volume. So they change shape and volume. Here's a table in your book that's a nice summary of all these properties. I'm not going to read it to you. So let's go on, and so that's classifying matter by its state. We can also classify it by its composition. So we're going to have a whole bunch of words here. A broad grouping is pure substance versus mixture. The key point of a pure substance is it's only one type of particle. If you look at it at the particulate level, all the particles are the same. So if we go back to the Lego illustration, you could make, a sculpture of maybe an elephant. If it was a pure substance, all the bricks would be the same. You made the whole elephant out of 2x4 blue bricks. Could you do that? Yes, you could. Now, it wouldn't be the best looking elephant, but you could do it. All the bricks are the same. In a mixture, we have 2 or more different types of atoms. So if you made an elephant and you used 2x4 blue bricks and 2x2 blue bricks, it's got 2 different kind of bricks in it. It's not a pure substance anymore. In a pure substance, all the particles are the same. Those particles can be atoms or they can be molecules. So here's an illustration of water. They gave us this lovely picture of water in a fountain. If we look at the particulate illustration, we see each particle of water looks like a little Mickey Mouse head, where his face is red and his ears are white. It's an oxygen and 2 hydrogens. These are molecules. Those atoms are bonded together in a particular arrangement. But all the particles in the water are exactly the same. In a mixture, that's not the case. So we have different kinds of pure substances. The type of pure substance that we call an element is one that cannot be broken down into simpler substances. So again, the Lego brick thing works pretty good. Can you break a Lego 2x4 brick with your bare hands? I don't think so. Could you cut it in half with a hacksaw? Yeah. So Lego bricks can be destroyed, and atoms can be smashed, okay? But not in ordinary chemical processes. That gets into nuclear reactions, okay? That's not something that you just can do in a lab like we have here. It involves a lot of effort and a lot of expensive equipment. So when we say that pure substances cannot be broken down into simpler substances, we mean in a normal chemical way. If you are just playing normally with Lego bricks, all the bricks that you start with are going to be all the bricks that you end with. They're not going to get broken in half. They're not going to magically disappear, although sometimes you think that special piece disappeared, but later you find out it was under the rug or something. But they can't be destroyed, okay, in a regular way. So all the known elements are listed in the periodic table. We've got a periodic table right up there. That periodic table lists 112 of them. Older periodic tables will list fewer. We keep making new ones. That's why they don't all have the same number. In your textbook, the inside front cover has a periodic table. The inside back cover has an alphabetical listing. So depending on what you're doing, one of those may be more useful than the other. So an element is an example of a pure substance. The other type of pure substance is a compound. What is a compound word? You should have learned that in elementary school. A compound word is a combination of 2 other words, right? Like underground. It's one word, and yet it's composed of 2 words, under and ground. So compounds are like compound words. They are 2 or more elements put together. A compound word is 2 or more words put together into one word. That just occurred to me right now. So this is a pure substance. two or more elements. Those two elements are in fixed proportions. Compounds are a lot more common than elements are. And you can take a compound and break it down into simpler substances. You can break it down into other compounds or into elements. So this is where I should have my Lego bricks, but I don't have my Lego bricks with me, so I'll have to draw you pictures instead. I know you love my pictures. Once we get rid of that. Okay, so, oh, that's right, I've got colors here. So let's do red. So here I've got a little red brick, and a little red brick, and a little red brick. And let's see, blue, that's not a very good Lego blue. This is a better Lego blue. And then it's got two blue ones on top of it. So imagine that we had these little tiny structures just made out of simple Lego bricks. But each of these is the same, and we had a whole substance made up of molecules that were like this. So all the particles are the same, all the molecules are the same. It qualifies as a pure substance. But could we, with ordinary chemical means, with just playing with them with our hands, could we take these apart into simpler things? We could. I could take this apart into two blue bricks and a red brick. I could do the same with all of these. So it's not an element, because an element you can't take apart. So this is, I didn't plan this out at all. This is a compound. Okay, and this, if all the particles were like this would be an element. So the difference is that the compound can be taken apart into elements. The element is already the smallest piece it can be. They're both pure substances, though. Here's, oh wait, we need to go back to that other slide to finish it. So compounds and elements are pure substances. A mixture is not a pure substance. A mixture is composed of different substances. So we've got different substances. But the key thing that makes it different from a compound is that the proportions can vary. So maybe I've got red bricks and blue bricks, but they're not bonded together in these little towers. They're just all random. I have the same pieces, they're put together in a different way. So I could have more blue bricks than red, or I can have more red than blue. The proportions vary. Here's an illustration of mixture. So air is a mixture. Air has oxygen in it, which is really important for us. And it's got nitrogen in it, and it has a bunch of other gases in it as well. But you can have different amounts of oxygen relative to nitrogen, and it's still air. It's a mixture. Seawater is also a mixture. We've got water molecules, these little Mickey Mouse guys, and then we've got salt particles in here as well. The water can be really salty, like out in the ocean, or like where a river joins into the ocean, you get some brackish water where you're transitioning from the fresh water in the river to the salt water in the ocean. And so the composition varies, and that's an important characteristic of mixtures. And then we can classify mixtures into two different groups. Isn't this awesome? You're like, We're going to have a table real soon that's going to kind of summarize all of this for us. So there's two different kinds of mixtures. We have homogeneous and heterogeneous. And again, those are prefixes that have meaning. Homo means the same. Hetero means different. So a homogeneous mixture has the same composition throughout. A heterogeneous mixture has a non-uniform composition. So let's think of some examples. Let's think of soup. It's not soup weather, but... So an example of a homogeneous mixture that would be soup might be just a simple broth. Oh, that's blue. That's okay. Or maybe tomato soup. Are there chunks in tomato soup? There's not supposed to be, right? Maybe you made it badly, but it's just smooth. And it's the same all the way throughout. Okay, a heterogeneous mixture is going to have chunks in it. So like minestrone soup, if you know what that is. It's got beans and noodles and vegetables. Or chicken noodle soup. You look at chicken noodle soup. There's little pieces of chicken, there's noodles, there's broth. There's different parts of it. It's heterogeneous, it's not all the same. So homogeneous means it's the same throughout. Heterogeneous has different parts. It's not uniform. So here's the table illustration. So we take matter and we can divide it into two broad categories, pure substances and mixtures. Pure substances we divide into elements and compounds. And it's really important to think at the particulate level. A compound has molecules that are composed of different elements. And yet, if we look at the particles, all the molecules are the same. That's what makes it a pure substance. Elements are going to have atoms, and all of them are going to be the same. And if you break it apart, you still just have those same atoms. You can't make anything simpler out of it. If we go over here to the mixtures, we divide mixtures into two groups, homogeneous and heterogeneous. And here they're using an illustration of tea. And they put this is sugar, they put some sugar in the tea. But the sugar dissolves and mixes all over throughout the tea. And the tea at the top of the cup is just as sweet as the tea at the bottom of the cup. It's the same throughout. And their example of a heterogeneous mixture is oil and water, kind of like Italian salad dressing. You can shake it up, but as soon as you set it down, the oil's going to move to the top and the water's going to stay on the bottom. It's heterogeneous. It forms layers. Okay, so important to understand those ideas. And then this is more... This chapter I didn't get edited as well. The person who wrote these slides, it seems like they almost just took the text of the book and divided it into slides. It's like, well, we might as well just read the book then. So my apologies for the rest of this PowerPoint presentation. This is just summarizing what we've already talked about. So it might be helpful to you to go look at it, but I'm not going to read that to you. Another thing we look at in terms of matter are the properties of matter. And again, we divide these into categories. They're physical properties and chemical properties. Physical properties are ones that you can observe or that a substance can display without changing its composition. So an example of that would be like its color or its density. So maybe the color of, I can observe the color of this pen. It's black. That doesn't change the particles of the pen by doing that. I can observe this piece of paper. It's white. It's 8.5 inches by 11. The size of it is a physical property. It has a particular density. Those are physical properties. A chemical property is one that a substance displays only through changing its composition. So, like flammability, that's a long word. Is paper flammable? Does it burn? It does. If I burn the paper, if I demonstrate the property of flammability, do I have paper left? No. The paper gets destroyed. It gets changed into something else. A chemical property, when demonstrated, alters the substance. And so now we're getting into some of these things that we were trying to do in lab, but we hadn't talked about them yet. So the characteristic odor of gasoline. I think you fill up at the pump, you just get a little whiff of that. Oh yeah, that's that gas smell. That's a physical property. When you smell the gas, you do not change its composition. The flammability of gas is a chemical property. When you burn the gas, when the engine in your car burns the gas, it changes the composition. It's not gasoline anymore. So you will be asked to identify, is this a physical property or a chemical property? And so you have to think about what are the particles doing and is it being changed or not? So the boiling point of water. When we boil water, do we change its molecules? We change its physical state. It goes from a liquid to a gas. When the students change from the liquid state to the gas state and leave the room, do the individual students change? No, you're still you, right? When water boils and goes into the gas state, all the particles are the same, but they're just farther apart from each other and not interacting with each other. Any of those state changes, the melting point, the boiling point, those are physical properties, the temperatures at which they do that. So it's still water when it boils. See, they just go on and on and on about this one idea. So here's a picture of a pot of water. And when it boils, see here we have the little Mickey Mouse heads. Here in the gas state, we still have the little Mickey Mouse heads. They are still the same. So that's a physical property, the temperature at which it boils. And then we have properties, we also have changes. And we looked in lab on Wednesday at the evidence for a chemical reaction or a chemical change. A physical change is one where the stuff doesn't change. The particles don't change. So state changes, where you're changing state, those are always physical changes. Melting, freezing, boiling, condensing, sublimation, deposition, all of those changes are just physical changes. The particles themselves are not being altered. So the matter changes its appearance, but not its composition. So changes its appearance, but not its composition. In a chemical change, the matter does change its composition. So the Statue of Liberty is kind of this greenish color, right? The Statue of Liberty is actually copper on the outside. So why isn't it the color of a shiny new penny? Well, because the copper reacts with things in the air and undergoes a chemical change, and then its color changes. And color change was one of those evidences of a chemical reaction. So when it undergoes a chemical change, the particles of the substance are changing into something else. The atoms are the same, but now they're combined in a different way. So maybe you had an elemental substance like copper, and now you have a compound with copper oxide, where the copper and the oxygens are bonded together to form molecules. So here's an example illustration of a chemical change. Iron rusts. In iron, we have these iron atoms, and they're all nicely arranged. And when it rusts, it combines with oxygen, and on the particulate level, it has been changed. Rusting is a chemical change. So when matter undergoes a chemical change, we call that a chemical reaction. A chemical reaction, a chemical change, those are two different names for exactly the same thing. And so we have a general way of representing this. Over here we list the reactants, because just like when we read left to right. So we do our chemical equations left to right. We start with the reactants. The reactants are the things that react. And then we have an arrow pointing that, it's going in this direction, and the reactants react to produce the products. Okay? Sometimes you may feel like we're trying to trick you with all these funny words we use. We're actually not, but other times they just hopefully make sense. The products are what you get, right? If you're in a manufacturing process, You're making boxes for them to put fruit in. Well, what's your product? Your product is the box. You took the raw materials and you did stuff to them and you made the box. So in a chemical reaction, we have our ingredients, our reactants, and they undergo a chemical change. We rearrange them, mix them up, do things to them, and then we get the products, and the products are different. It's a chemical change. Again, this is just going over and over the same stuff. So bottom line, when you're trying to identify, is this a chemical change or a physical change? Think of the particulate level. What's going on in the particles? Now, if I take this piece of paper and I tear it in half, and that was the key, that wasn't someone's quiz. If I tear it in half, have I changed the paper? Well, some of its physical properties have changed. It's not the same size anymore, is it? But are the particles in the paper still paper particles? They are. That was a physical change. If I take this and I burn it, which, one of these days I should have my act together and actually do that, because that would wake some people up. If I burn it, that's a chemical change, because now I don't have the paper anymore. And so those four evidences, the bubbling and the energy given off or taken in, the color change, the solid forming, those are evidence that we can see or feel of a chemical change, that the particles are changing. Here's another illustration. This one's kind of nice, though. I like this one. So here's an illustration of a butane lighter. So here we have these little butane molecules, and they're in the liquid form in here. If you just open this without striking the flint, you can't really tell, but the butane will come out. It will escape into the gas state. Look at those particles. Do those look the same as the ones in here? They do. Here they're in a liquid state, here they're in a gas state. That's a state change. The particles don't get changed, they're just moving a little differently. They're not as close to each other. So that's a physical change. If we light the lighter and we have a little flame here, this is a chemical reaction going on. What physical evidence do we have from those things we learned in lab? Is there any heat being given off? Yeah, when you burn the butane, it gives off heat. So energy was given off. That's evidence of a chemical reaction, because we can't really see what's going on, but here we're illustrating it. So here we have those butane molecules. They are coming into the gas state here, but now there's a flame. The flame is the reaction of them changing into carbon dioxide and water molecules. They're reacting with oxygen in the air, that's where those red ones came from, and they're making a new substance. The particles have been changed. It's a chemical change. Okay? One thing about mixtures is that we can separate them based on differences in their physical properties. I'm actually going to skip to the next one because it's a little more obvious. I made spaghetti last night, and at my house we make 2 pounds at a time and hope that there's some left for lunch. So you boil the spaghetti in the water. You have a mixture of spaghetti and water, because you could put 2 pounds of spaghetti in that pot of water, or you could put 2 ounces of spaghetti, just a little bit, because you're a person who eats like a bird and you're eating alone and you're just going to make enough for your supper. It's a little tiny bit of spaghetti. We don't know how to do that. So here you have a mixture, and then you want to separate it. How do you get the spaghetti out of the water? What's the fastest way to do it? To strain it, right? Use a colander. It's like a big bowl with holes in it, if you didn't know the name of that one. It's the big bowl with holes in it, and you put it in the sink and you dump it all in there. The water is a liquid. It can go through the holes. The spaghetti is solid. It can't go through the holes. Differences in physical properties allow us to separate the mixture. That's called filtration. Okay, so here's an illustration of a filtration done in the lab. We use a funnel with a filter paper, and that's a lot like a coffee filter. It's just got little tiny holes, and the water can go through, but the solid that's mixed in here can't go through, and so you can separate a solid from a liquid. Another way of separating mixtures is called distillation, and this is how alcohol is made. To make alcohol, you take some substance that has sugar in it, whether it be grapes or barley, hops, or I don't know what they make all those different things out of, and you ferment it. Bacteria and stuff turn the sugar into alcohol, and so now you've got alcohol and water. And usually for wine, you just filter out the solids, and you're good with that. But if you want to make something more concentrated, distilled spirits, then you need to get the water out of there. And one way to do that is distillation. Distillation works based on the differences in the boiling points of these two liquids. It's a way of separating liquids. So you heat the mixture of liquids, let's just say alcohol and water, and the alcohol is going to boil, it's going to vaporize at a lower temperature. So the alcohol vaporizes, and the water isn't hot enough to vaporize yet. The alcohol vaporizes. We don't let it just escape into the atmosphere. We catch it in this tube and we cool it down, and so it becomes a liquid again and drips down into here. And so we're able to separate those based on the physical property of boiling point. In this process, the particles don't change at all. It's the same as filtering spaghetti, really. We're just separating them based on physical properties, and so nothing actually changes. Mixtures can be separated. Sometimes it's a challenge to figure out exactly how to separate them, but they can be separated. Compounds cannot be separated by physical changes. Okay, 3.7, conservation of mass. There is no new matter. All of the matter that is in the universe is already in the universe. There's no plant somewhere that's manufacturing carbon atoms. So a basic principle that we have is matter is neither created nor destroyed. And then we have this little caveat here, this limitation, in a chemical reaction. Okay, matter can be created or destroyed in a nuclear reaction, but that's a subject that we're not really going to touch on in this class. In nuclear reaction, you can get changes in mass that are significant. But during regular physical and chemical changes, the total amount of matter remains constant. So here's an example. Thinking back to that lighter. If you have 58 grams of butane and you burn it, it's going to combine with 208 grams of oxygen. So the total amount of substance, of matter that you started with is 266 grams. After you burn it, you're going to end up with 176 grams of carbon dioxide and 90 grams of water. So we've changed what it is. We've changed it into other stuff. It's a chemical change. But we add those two numbers together and we still have 266 grams. It's like when you're playing with Legos. If you take a car and a house and you take them apart and you make a truck and a bus. Did you have Lego pieces that just appeared out of nowhere that were created? No, you wish that could happen. Did you have Lego pieces that just vanished? No, they can't be created or destroyed. What you have when you start with is what you end up with. All we're doing in a chemical change is rearranging the atoms. And that's a good place to stop. So we'll pick up there on what day? Monday.